All right, for your worksheet part, you're going to need this software, HNMR Molecular. It's developed by NC State. It's an educational app that they put together. So Dr. Oliver Hoyo and her former graduate student, she's now a PhD, and she actually has a job now doing something similar to this. She actually worked on this and put together this app. It is an app that helps you use augmented reality to explore NMR. So get the app, do it now, pause the video, go ahead and get it on your phone. And then in lab, you're going to explore this in your group.
So in your assignment, you're going to be able to see the behavior of some of these molecules by following along with what they're saying. And so you're going to work together in your groups and use this AR technology to help you with NMR.
For this week, we're going to do NMR. I mentioned before there is software that's in the organic lab on the IR computer that can predict NMR. And it's actually a little bit more detailed than Spartan is. So you can get some more help for that. But it can also do other things. You can draw a structure, so you can draw your structures in there, and it can put it, you can ask it to put it in correct formatting, because there's correct formatting that you need for our drawings that we need to have. We can use it to draw glassware. There's some templates for glassware. There's TLC plates where you can just put in the RF and it will put in where all the spots need to be, etc. But it can also predict NMR data, and it can predict it with it's generally pretty close, and it's usually a little bit more clear than the Spartan is. So I'll take you in groups to kind of show you that while you're working on the first couple of things. So I will be talking you through at least how to work through the limonene NMR that you ran. So I'm going to let you guys work on that and try that, because then you're going to have to be on your own for your unknown. There are videos that go through every single step of the Delta software, and most other software are going to be very, very similar to how they work. The buttons just might be in different places. So if you're going to use other software, please, please, please use their help buttons and things like that in addition. So we are going to interpret our limonene, and there is some information in your ELN that you're going to fill in. I'm going to do some of it and you're going to fill in the rest. But let's kind of start first, and then I'll open the NMR and take a look. If we have proton NMR and carbon NMR, let's talk about the things that you should see. And remember, you also have depth. So if we start with, we see that we have all of these methyl groups. I'm going to call this B, for instance. In your notebook, they're labeled different. A and B are methyl groups. On the carbon NMR, we're going to see the methyl group somewhere between 0 and 100 ppm. I'm going to say they're probably closer to the 50 mark, just because they're close to pi bonds. And so because they're close to pi bonds, I would say they're probably somewhere in the middle, or a little bit closer to the other side, but they're not like all the way close to 100. So what we'll see on the depth is that because they're CH3s, they're going to be positive, they're going to be pointing upwards. On the proton NMR, we're going to see for each one of these, they don't have any neighboring hydrogens, so they're going to be singlets. So there's no neighboring hydrogens for A and B, so they're going to be singlets. They're going to be showing up somewhere between 0 and 4 ppm. I would say they're close, probably close to the 2, like 1.5 to 2 mark probably. And in terms of integration, when we integrate them, when we find them, we can set them to 3 hydrogens, because we know that they're supposed to be 3 hydrogens, right? So that's the thing with integration when we're using the software. If we already know what our structure is, we can pick something that we know what the peak is, and we can set it to the correct integration. So I'll show you that. However, if it's an unknown sample, you may integrate everything and then figure out what the ratio is later. So these CH2s, well, that's not a CH2, but this CH2 here, these CH2s here, I'm going to call them C's. They're not all identical, by the way, but I'm going to call them C. They're CH2s. They're again going to be showing up between about 0 and 2 ppm. They're going to be, because of what they look like, you might predict that this one here might be a triplet because it's next to this one, and this one would be, this one here has 2 neighbors next to it, plus this one to be a quartet. But they're kind of close to each other and they're overlapping each other, so you may actually see these as multiplets. They may all overlap each other. They're not all the same, but they may overlap each other, because what you might end up seeing is that all the peaks are kind of like all on top of each other. So if you have your quartet, your doublet, your singlet, whatever, and then just end up looking like they're all on top of each other. So you're going to end up seeing something like that. Now for this hydrogen here, this is going to also probably, you're going to have 2 neighbors here, 2 neighbors here, 4. So that will give us a quintet. But because this is kind of a diastereotopic proton, it may not appear quite, so I'm going to call this D. It may not quite appear as a quartet, but in reality, it should be kind of like a quartet. Oh, and I forgot with C, if they're all overlapping, if you integrate them, they should come out to be about 8 hydrogens altogether, because they're going to overlap and you can't distinguish them. This would integrate for 1. Once I've set these first ones to 3, then they all should integrate correctly for you. Then I have a hydrogen here, which I'm going to call E. E has 2 neighbors, so you should see this as a triplet, but it is in the double bond region. So because it's in the double bond region, it's going to be showing up between 4.5 to 6.5 ppms. And I'm going to call this D. There's no EF, F. There's no hydrogens on this location, so on this one, F, it has no neighbors, so it should be like a singlet. And it will also show up kind of in this range. Now, when we go to the carbon NMR, we'll see that for the C's, they should all show up somewhere between roughly about 0 to about 50-ish. They're all CH2, so on the depth, they're going to be negative. The D is a CH, so it's also going to be between the 0 and 50 mark, but it's a CH, so it'll be positive. The E is, so this is D, C, A, and B. The E is going to be on the double bond, so that should show up between 100 to 150, and so will F, except that E will be a CH, so it will be up, and F is a CH2, so it will be on the depth as down. So when we look at the depth, you'll see it's down, and so that's how we can figure out what they are.
First thing that I want you to note, pay close attention. This peak in the 77s, that's not a part of your molecule. That's actually chloroform D. It will show up because it has a carbon on it. So CdCl3. We can't help it. It will show up there. You don't need to do anything with it when you're actually in the lab. I'm actually going to remove the numbers on there. You will have to put numbers on there more likely than not, and we use this little symbol that looks like a diamond with a dot in there, and you click on your peaks and the numbers you go in. So I'll show you in just a second. So again, please write this down, that what this looks like is 3 little peaks. It kind of looks like almost like a triplet. It's not a triplet. But if I click on a peak, you'll see, but you have to click right on the peak, and sometimes I can't see exactly where my mouse is because it's yellow. I don't know why I changed it to yellow, and I don't remember how to fix it. So we can click on them and you'll see the numbers. Now, because we're going to be comparing carbon and depth, so I know that I have a peak at 20.8 something. I'm going to move this aside. I'm going to open my ELN. I would put, I'm going to have this kind of side by side. So I can go ahead and put that this is 20.8953 and 8. That was not supposed to be a 5. All right, so now we want to look at our depth. So when you first open Proton Carbons, if you're using version 4, you have to process the data. So for carbon and depth, carbon and auto process for proton is this. Now, if we were to look at our derivation from Spartan, it's pointing downwards, and that's because if your sample is too concentrated, it causes all your peaks to actually flip, and we can actually process it to fix this. And so I can, there's something called phasing. I can rephase it so that it goes in the right way. So there we go. So I can see that first peak, that's around 20. There's a CH3, which should match what we have here. So on my depth, it's positive. So it's pointing up, which could mean that this is a CH3. We already know it's CH3 because of our Spartan, but you can use that. So if I look at this, if I look at my Spartan predicts that that first peak closer to the lowest number is actually this one coming from here, which on my molecule is H. I can probably say this is H. And then if I go to the next one, which on my deck was also pointing up, 23.573, I can do the same thing. And I know it's a CH3, and I'm going to actually fix these 3's, by the way. I'm sorry. Underscore. So this would have to be that other one, which I'm going to put K. Okay. So we basically do that for everything and interpret everything. So I'll have a more full video for this in your notebook as well. But the next thing that you're going to need to do is figure out how to write this the way that we normally put in our reports. Now, the format that we usually use is what instrument it is, type of instrument, like megahertz of the instrument. Ours is 300, the solvent that we use, and then you put the shift and what derives, and it goes in the order of highest number, so downfield to upfield. So, for instance, I would have 23, I don't have all the numbers in, 23.573 as like the lowest things. And in brackets, my derivation is that it's CH3. And you can describe where that CH3 is very briefly, like if that CH3 is attached to a CH2. But in this case, to make it easier, I just put letters because in this case it's A, right? Just because I put letters on my structure. If I did that for like a publication, you wouldn't do that. But for your lab reports, you could do something like this, and then 20.89, blah, 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 blah. I'm not going to write the whole thing in. It's a CH3, and we said that was H. And so we could use this information to fill in our tables. We do the same thing for protons. So again, I'll have a kind of a talk through, especially the proton, and then you'll do this to finish this up in lab, or you can do it outside lab if you want. So again, the proton NMR may not be processed for you, especially depends on the software, so you have to hit proton auto process. If it's already like this, then it wouldn't matter. I do want you to note something on here. I'm going to zoom in. So chloroform D shows up on your proton NMR. There's very little of it in my sample, so it's a little hard to see. So chloroform D shows up at 7.26, and you see I have a peak at 7.26. This is actually chloroform D. It's not D anymore because if there's traces of solvent, of water in the air, chloroform B will become CHCl3. So instead of chloroform D, it's just chloroform, and it will show up on your NMR. So it doesn't, notice it was tiny because at the time this was a brand new bottle that I had. There was not much water that got into it. The solvents that you are using as well for your NMR may have the standard in it that shows up as around 0. This one that I used did not. And so for this, you're also going to be, and I'll start with these peaks down here because these are on double bonds. I can integrate these two and notice that these numbers are really high, but I can figure out based on my structure, if I go back to my NMR, I can figure out what some of these peaks are. So this is this hydrogen coming off at 5 point something. Then you have these protons coming off here. They're showing it like it's a doublet because these are technically diastereotopic, but they're so close to each other that they just look like a broadened peak. So it's saying that this is the lower ppm value one. So if I go to my proton NMR, the one that's that lower number around 4, we know it should integrate actually for 2. So I can actually set it to 2. And when I do that, oops, I said the wrong one, I'm sorry. So set this to 2, notice that this is about 1, which the other proton was about 1 on our structure. So if you look at your structure, so once I integrate 1, all the others will integrate. Now, when I talked about this a little bit before, I also mentioned to you that you're going to see a whole lot of junk and multiplicities here, but you're going to see some singlets. So your singlets are going to be easier to interpret, but they're kind of a little bit overlapping with things. With the multiplets, you're just going to have to try your best to interpret them. So later on, the video that I'm going to post in your notebook that you want to look at will kind of talk you through how to do some of this. So yeah, so that's kind of what you would do with the NMR. But in your notebook, you're going to put the shift, you're going to put the splitting pattern. So is it a, like we saw something like at 4 point, and this is not necessarily the order you write it in, 4 point whatever ppm, and our splitting pattern was a singlet. When we integrated it, it was 2H, and we could derive that was, on our molecule, it actually turns out that it was G, the hydrogen's on G, so that was a CH2, and those were G. And you would do the same thing for the rest of them. Now, when it comes to filling out this information, we'd do something similar. You would put, and again, you'd go from the highest number to the lowest number. So I know that, for instance, if this were supposed to be here, I don't remember exactly what it's supposed to be, something like that. My multiplicity would be a singlet. Oops, I need to delete that 4. And then the number of hydrogens that I have is 2 hydrogens. And then my derivation is, let's say I say CH2-H. For example, to kind of tell whoever is looking at it that that's what we're doing. Now, if you don't have a structure with letters matched to it given, those letters don't mean anything. So for a lab report, I would always draw your structure and label it like I have here. In a publication, you would have to do something like the CH2 and then show that this is attached to a double bond of some sorts. Like you would put something else, but you would underline that hydrogen so that people know that that's what you're talking about. So let me give you an example. So instead of saying that the derivation is H, this could have been a CH2. I put an underline here, and then maybe I have like something that represents this on the double bond to a carbon, something of that nature. That's how papers usually do this.